We have seen a model of this kind. Log of the data, which is another data, is equal to a constant, a parameter, log of a, which I call a prime, plus alpha ti plus epsilon I. This is an example of linear regression. So the next important thing to know is that if you have linear regression, then good news, there are closed form expressions in matrix form for doing the estimation. So we will not have to do to solve a complex optimization problem. So the model 3 that I've just shown is a special case of linear regression. In general, a linear regression model is of this kind. By default, when people say linear regression model, practically invariably, they mean with least squares. So it means exactly this model. The error term is IID Gaussian, n0 sigma square. And the dependency of the explanatory part of the model with respect to the parameter is linear. Right? It doesn't mean that the growth is linear. For example, we had exponential growth rate, but it means that with respect to the parameter, whatever you call the parameter, the thing is linear here. Right? So for such a model, which I write now in this form, because it's linear, very often the dependency on the parameter is called via a matrix, so it is called the design matrix or the X matrix. So the ith data is equal to a matrix multiplied by the parameter b, and the matrix is supposed to be known. So the fi is now x here. So this is known, but what is not known is beta, right? We assume, of course, that the model makes sense, so x has a rank which is equal to the dimension of the parameter here. Otherwise, it means the model is not well specified. If there are multiple parameters that give the same model, it will be impossible to find what is the parameter model. So that's an assumption we must do, but it's not a limiting assumption. Once we have that, then here is the theorem that gives the solution. It says that there's an important matrix, projection matrix, which is x transpose x, that is always invertible under this condition that I mentioned before about identifiability of the model. And then the maximum likelihood estimator, which was the solution to a least square minimization problem, is obtained by computing what is often called a K matrix, which is this inverse of this projection matrix, and of this, it's not a projection, otherwise we would not have an inverse. The inverse of this important matrix times x transpose. So everything is derived by those magic formulas from the design matrix X. Right? This is also sometimes, this is called a K matrix, and very often that's the only thing we're interested in, but if we want confidence intervals, we have a bit more. A few things about the residual. The residual, we call residuals the errors once we've done the estimation. So y is my data, x b hat is what I estimate the true thing would be. So the difference between the two, the ith coordinate, is the ith coordinate of my error. That's what we did in the previous example here. Now, if we do this, we obtain residuals that are zero mean Gaussian, but are correlated. So they are not exactly the noise, because the noise would be independent. They are slightly correlated. They're a bit correlated here. Why is that? Well, the correlation comes from the fact that they're estimated from the same data here. But the correlation can be computed. The correlation matrix is given by an H matrix, which again depends on the matrix X of the design. And if we want to be extremely refined, we can do what is called a rescaling of the residual, because the H matrix here, if I look at the diagonal term, I will have 1 minus the diagonal element of H. That's the variance of EI. So the variance of each of the residuals after estimation is not always the same. Right? They're not all have the same. There is an explanation for that. If you have a cloud of points and you put a line in the middle, right, then the error is probably going to be less at the edges, because when you try, if you vary the line, it's easy to make a line that does not. If you vary like this, then you'll have a big error at the edges, so you will turn it, right? So the residuals at the edges are likely to be smaller than in the middle, where if you have whatever you do, the things in the middle has to go through the middle here. In estimation theory, it's called leverage. So if some residuals have very little variance, it means that no matter how you estimate, your model always passes exactly through this point, which typically means that you don't have in this point, there is no redundancy in the system. And estimating this point is, whatever you estimate, the value will always go exactly through this point. If you want to estimate a straight line, if one of the points is incorrect, it will affect the estimation, but there are the other points that will force the estimation to be somewhere. So if one of the points is in error, the other points will help detect that this point is in error, because if you have an outlier that's outside the line, you think, oh, this was an error, let me correct it. But if this is a leverage point, such that the estimation will always be exact at this point, that it's impossible to estimate this error. So this is related to whether a point in our set of data point is in some things collectively related to the other points, so that if it's an outlier, it will be detectable, or not. If not, it's called a leverage point, and it's bad for you. In data science, we should avoid to have such things, but if it happens, it will be visible by the fact that the standardized residual will tend to be extremely small here. For us in practice, it may mean, very often this is not done, but if you have enough time and accuracy, we should do that, because then we can check the model by checking whether the Ri are approximately Gaussian here, because at least those ones should have unit variance here. Let's do it a bit later. So that's about the residual. We are interested sometimes to find, and often hopefully to find, confidence intervals. Then by application of the previous result I gave before I gave a generic result for finding confidence intervals, assuming we have found the estimated beta. Now I know also what is the estimated beta, so I can find confidence interval in closed form by computing things that are derived from the X matrix. From X we get K. I compute K transpose, and which is the same as X transpose X inverse. So this G matrix is called is used to compute what is the variance bias. So if I use the terms of the G matrix, if I need to estimate a linear combination of the parameters, in particular if I want to estimate any coordinate of the parameters, then I have a pivot by saying the true value of this linear combination minus the estimated divided by the S. S is the estimate of the unknown variance here, rescaled by square root of G, which is a parameter that we had found, for example, before the break. We had said there was a square root of I, square root of things that involve T bar, etc. So those are all those terms that can be captured in closed form in general with this matrix explanation here. So take-home message, if you have a model of a linear regression model, use a package that will compute all of this for you. Or in fact, all you need is to be able to write the X matrix. That's the only thing you need. Once you have the X matrix, this is all 3-4 lines of scripts to get everything here. For example, here is Joe's shop of the first homeware when there is congestion collapse on the wireless LAN access. Assume we would like to explain that by a performance model that would be saying, as a function of the offered load, here is the achieved throughput. and I think there is congestion collapse, so it increases linearly up to a turning point where it starts decreasing. So the turning point I call Xi, and my model says the y value that I read here is equal to a function of the x value, which is a linear function, a plus b xi, which is true only when xi is the values on the x-axis here, which is true only when we are below the turning point in the x-axis, so it's given by this formula. The 1 with an index means this is 1 if the condition is true, and is 0 otherwise. Plus something else here, with a constraint that the two lines here, the two straight lines, they make a continuous curve, so they have the same value here, which is given by this constraint here. And I assume that there's a straight line plus IED noise. Well, at least that's one model I'm doing here. This is an example of a regression model. Is this a linear regression model, by the way? Majority says A, which is a bit optimistic. Then the second vote is C, which is wrong, so the correct is B. So this is an exercise in mapping a general theory to what is the purpose of this course, modeling, using it in practice. So let's look in detail at the practice here. The answer is yes if the turning point is known. So let's assume the turning point is known. What does it mean to be a linear regression model? It means here, the tricky thing to understand is we're trying to fit a model on the y-axis versus the x. So when we do that, we treat the x-axis as known, even though in some other modeling exercise, we might treat the x also as random. But here we don't. We assume the x is known, and the y is some function of x plus noise. That's what it means to do the fitting. There are other fitting models called total least square, where we will also treat x as unknown, but that's a different story. Here, if we do linear regression of this model, it means the xi are known and not treated as random. And now the question is, the explanatory model for y that corresponds to x, does it depend linearly on the parameters? And the question is, for each coordinate, is it linear in the parameter? So if I look at the first xi for x1 is less than 70. So the formula is for f1, the true value that we would see if the model would be perfectly exact, is a plus b x1. Does that depend linearly on a and b? The answer is yes. It doesn't depend linearly on x, right? Because there is this condition which is nonlinear on x, but that's not the question that's asked. The question is, the x are considered as fixed things that are not to be estimated. With respect to the things we try to estimate, is the dependency linear? The answer here is yes. The pawns are known, so each of the fi here is depending linearly on the parameter a, b, c, d. Of course, Xi needs to be fitted as well, and then we have a nonlinear model that we will discuss in a second. So if I ask MATLAB to solve for that, I will obtain this. Here I've fixed the turning point to 70, and I've obtained coefficients for A, B, C, D with confidence intervals, because the theory gives very easily confidence interval. The big thing I need to do here is to find the X matrix, right? The X matrix is obtained by writing that. So the first line of this X matrix, the X matrix is obtained when you write Y as a function of the parameter. So the first line is for Y1. So the first line of the matrix will be A, B, X1, and then 0, 0, because the X matrix tells you how the first Y depends on the 4 values of the parameter A, B, C, D. Though, or the 3, because there is a relationship between A, B, C, and D. So we'll have an X matrix that has as many lines as there are data points here. If you have 1 million data points, you have a matrix with 1 million lines. So then you need MATLAB for big matrices, right? Or Julia rather than MATLAB for things like this. Here I plotted the residuals and the standardized residuals. So the standardized residuals are the blue ones. We see that they're a bit smaller than the residuals. Is it a valid model? Well, we could make one criticism. Which one? Does it appear to be Gaussian? I did here a QQ plot, which is so-so. It's not extremely wild as the one we had before, but we see here, clearly we see that the variance is increasing. So it's smaller on the left than on the right. So we could use perhaps, like we did in the very first example, we could refine it in a better model, but I didn't do it here. Instead, what I did is to solve the nonlinear parts. So there is a second addendum to what I saw before. So the first take-home message is, if you have a linear dependency on the parameter, blam, there are big, you use the power of linear algebra to solve your problems. If you have nonlinearity with respect to a small number of parameters, there is another trick you can do, which is to use this last statement in a theorem that I skipped a few minutes ago. The theorem about linear regression says that this quantity here is a pivot. What is this quantity? If you remember the derivation we did an hour ago to explain why least square is the same as the model that assumes IID Gaussian noise, right? I did the derivation of computing the maximum likelihood. And we saw that the first step is saying, if I know beta, what should sigma be? And then the beta should be the one that minimizes the log of the estimated sigma here. So this is exactly what I'm doing here, but there is another information about this with this statistical model, which is only approximately true and is true when the number of samples is large. It relies on the central limit theorem, like we saw for estimating the mean of a sample. It says that the distribution of this is chi-square, right? Whatever the value of beta, whatever every other value thing of your parameter here, when you do this difference, when you're trying to find the beta by looking at the log of sigma, so at the optimal value, you will find ln here is the natural logarithm, is what I wrote as log a few minutes ago. So we will look for the beta that minimizes this here, right? So, and that gives us the sigma hat, the true estimator of our maximum likelihood estimator here. Right? So let's see how this is used. I computed here for every value of xi, I can compute the parameters a, b, c, d. I removed c because there's a relationship between a, b, c, and d. If xi is known, the relationship is due to the fact that we want that the two lines merge at the break point here. I did it previously for xi equals 70. Here I did it for all value of xi's between 10 and 90. And for all values of xi between 10 and 90, I plotted the value of this score function here, right? I plotted the value of the log likelihood when everything is optimal except one value, which is here xi. So I fix xi, I solve the optimization problem, I compute the sigma hat that results of the optimization. This is all given by the closed forms, and I plot in the y-axis the log of the sigma hat here, or minus log of the sigma hat here. And the maximum likelihood estimation is the one that reaches the maximum. So the xi, the best xi, the maximum likelihood estimator of xi is the one that reaches the maximum. What did I do here? I solved a nonlinear optimization problem by breaking it as follows. If I know xi, I have a linear optimization problem. So I compute the score that I want to minimize or maximize when Xi is given. I have to maximize the likelihood. Here I plot the likelihood for any value of Xi. If I know Xi, the other parameters are given in closed form. So one shot, I find them and I plot them. And therefore, I'm solving a maximization problem by brute force because it is low dimensional. I discretize, find all the values, compute all the values, and find the larger one. And it gives me that the larger value within the accuracy that it gave, I looked only at integer values, is 77 here. So 70 was not a bad guess, but 77 is the maximum likelihood estimate. But this theorem tells me more. It says that with probability 95%, I will find error bar by saying that with probability 95%, the true value on the y-axis, I find the magical value that was given here, 392. So I put 392 here on this axis. And with 95 probability, a confidence interval for Xi is given by the value that are between the two here. So my estimated Xi minus the log likelihood of the true Xi, which is L is the function I've computed here, with probability 95%, sorry, it's 1/2 of the value I gave before. With probability 95%, this is less than here. So in other words, this quantity, L of Xi hat, so L is a function that I don't know in closed form, but I can compute it. For a value of Xi, I can compute it by applying the linear regression formula. So this function L, which is well defined, though I don't have a closed form expression for it, is a pivot for my unknown thing. The difference between the two has a chi-square distribution. Therefore, in fact, it's 2 times this has a chi-square distribution. This is why I divide by 2 here. Therefore, with probability 95%, I am in this range. So another magical number here. So I need numerically to invert by drawing the straight line. I ask MATLAB what is the x that corresponds to that, and I obtain a confidence interval 7380 here. Voilà, that's the second trick. And with this bag of tricks, if it's linear, they are closed form. If it's nonlinear with a small number of dimensions, then by brute force optimization, we will obtain the maximum likelihood estimation. And we can find a confidence interval by putting a bound around the top of the estimation here. So this is all we can say, at least easily, about linear regression. Before we dive into nonlinear regression, non-least square regression, if you look in numerical packages, you will find zillions of least square estimations. They have names like ANOVA, ANOVA this, ANOVA that, ANOVA. They are all applying exactly the theorem that I gave to you. They're all variants of that. The only difference is when there is some structure to your model. The most general dependency is there is a big X matrix that depends on your parameter. Now, in some cases, your X matrix is, you can write it in a smarter way instead of having to write explicitly the X matrix. So all those packages that are doing linear regression with least square, the only thing they're doing is they are pre-processing for you the X matrix, right? In other words, you can forget about them. You know, the only thing you need to know is the generic theorem. So that's the good news about linear regression. It's extremely powerful. There's only one result to know, and with that, you can solve any problem. Now let's move to another form of estimation which is not least square, but using L1 norm. Before going there, let's introduce yet another distribution. A bit later in the course, we'll talk about a class of interesting distributions. We've seen the Gaussian, exponential, uniform, and in the homeworks you've seen played with a number of others. Here is one of interest, which is called the Laplace noise. It starts from the exponential distribution. recall that the exponential distribution, one way to think about it is to say that its PDF is given by that. It's exponential minus x if lambda is equal to 1, and if for general lambda, lambda exponential minus lambda x, and it takes only non-negative values. Right. Its CDF is easy to remember, or in fact 1 minus the CDF, the probability that the random variable takes a value larger than c, is exponential minus lambda c. Here. And it has a very nice property, which is it's memoryless. Right? Now, let's consider the following simulation exercise, which is I draw y according to this distribution here. Then I draw another u. I flip a coin. If u is less than 0.5, which means probability 0.5, I say x is equal to y. Otherwise, x is equal to minus y. Okay? So I draw an exponential random variable. And with 50% probability, I keep it. Or with 50% probability, I put the minus sign in front of it. In other words, I put a plus or minus 1 in front of it, which is uniform between plus 1 and minus 1. That thing is called Laplace noise. Right. What is its PDF? And the overwhelming majority says B, which is correct. Good. The next question is, how do you prove that? Well, let me do it in two forms. One intuitive, which is the one I prefer. Another one which is formal and rigorous, which might be needed if you write a paper or if you're not too sure about your intuition. So let Q be the random variable that returns 1 or 0 when we choose the first alternative. So Q is independent of the y that we've drawn. And what I'm interested in is the final outcome x. So for an x positive, let me compute the probability that capital X, the final output, is close to x. So is an interval x plus dx. Right? This will be equal to the PDF times dx plus terms that will be of order 2 or negligible with respect to dx. Right? Now, what does it mean? If x falls between x and x plus dx, so little x is a number, for example, 1. What's the probability that the output is between 1 and 1001? Well, this event saying that the output is equal to that, certainly if that happens, it means we picked the plus sign. Right? So Q is equal 1, and the exponential variable was between 1 and 1001. So what's the probability of this? Those two events are independent because Q and Y are drawn independently. So the probability of this is the product of the probability. So it's 1/2, and that is the probability that this random variable falls there. So when x is positive, Fy of x is 1/2 lambda exponential minus x. Right? When x is negative, we have the same thing, except we will fall between x and x. For if x is equal to minus 1, that means that the y we had first, the sign we obtained was minus 1, so Q is 0, and the y we had obtained was around minus 1. That occurs also with probability lambda exponential minus lambda, so I put the absolute value to remove the ugly minus sign for something that is positive, because x is negative, so minus x is positive. So in that case, we have 1/2 of this here. So if we look at the two together, when x is positive and when x is negative, I find 1/2 lambda exponential minus lambda, absolute value of x, because here x is positive, absolute value of x is the same as x. And when x is equal to 0, those two values give the same, so I'm happy too. So this should be the density. If I want to be formal, not that it's so important to be formal, but I think it's a good opportunity to introduce these methods to verify a formula. It's not a method that will always be very helpful, although we will see with PAM calculus there are cases where this method can give us even the formula. In probability, we reason about PDF or CDF, right? That's the classical way to reason about it. But mathematicians, where they think about probability, they have a more abstract way of reasoning about it, which is useful also practically. It is to a probability is given if I am able to, the distribution of random variable is given if I can compute the expectation of any test function of the random variable. And in fact, when we compute the CDF, it is the same as taking test functions, where the test function is the function that is plus 1 between minus infinity and c, and 0 above c. So if I take this test function, which is a discontinuous function, right? The expectation of this test function is the probability that x is less than or equal to c. If I know that for all c, I have the distribution. So I'm not forced to do that for any test function, but instead of writing CDF and so on that are always a bit clumsy, I can say, let me do it for an arbitrary test function, right? And then the expectation of phi of x is equal to the integral, if x is a real valued random variable, the integral of phi of x times the PDF, right? And the trick is to say, if I can write this in this form, for any phi, so phi or a large class of phi, this must be the PDF, right? So that defines the PDF, in fact. Right? So let's do it. I want to compute the expectation of phi of x. What I can easily do is the computation, the conditional expectation of phi of x given q equal 1. So given that the sign we have taken is plus 1, then given that x is an exponential distribution. So I apply this formula in the reverse order. Given that x is equal to y, so expectation of phi of y, I apply this. This is sum from 0 plus infinity phi of x lambda exponential minus lambda x dx, right? Which is also the sum as the same as if we take the absolute value here, right? Now, if I take the given q is equal to 0, I will have similar thing, except x is equal to minus y. So I apply the same formula with the test function of y is phi of minus y. So that's the probability 101 formula. This is the expectation of this, right? I'm just recognizing here the PDF of an exponential random variable. Then I change variable in the integral x minus x. This is the same as integral from minus infinity to 0 of this, which is the same. So the x changes sign here. So this appears to be positive, but because x is negative, I make it obvious here by introducing the absolute value here. So I have the two conditional distribution. And, well, why is it finished? Well, it's not exactly finished, but, well, my proof is finished, at least. Then, if I want to find what is the expectation of phi of x, then it is with probability 50%, it is this. That's the law of total probabilities. So it's 1/2 of this plus 1/2 of that. So it's 1/2 of this integral plus 1/2 of this integral. Now, if I can merge the two integral, that means that is 1/2 of the integral from minus infinity to plus infinity of this with the absolute value, which was the form we had before. So take-home message, the Laplace noise, we can interpret it as exponential noise with equal probability. We put a plus or a minus sign in front of it. And here is the PDF. The PDF is obtained by, in fact, taking the PDF of the exponential distribution and symmetrizing it and dividing by 2 so that the total mass remains 1. I plotted it in red here. So this red curve, if we forget the 1/2, would be the PDF of the exponential distribution. Now I symmetrize it, I obtain the Laplace, and I've compared it to a normal distribution that has the same mean, that has the same variance, sorry. The mean is 0 for both, they're symmetric, but that have the same variance here. If we compare both, what do we see? The Laplace noise decays way more slowly than for the Gaussian noise. So if we assume the noise is Laplace, which we will do soon, it means that we accept more easily that there are large values here. The Gaussian distribution has a support that is infinite. Any value between minus infinity and plus infinity is possible. But the probability of finding them decays like exponential minus x squared, which decays incredibly fast to 0. Right? Here it decays fast to 0, it's exponential, but not square, exponential minus x. So it decays much less fast. That's the trick. When we have Laplace noise, we allow large values more than with Gaussian noise. This is why it will be more robust. It means if there are a few values that are very weird, the Laplace noise will say, yeah, it's possible, it can happen once in a while. Whereas the Gaussian noise will say, oh, it's impossible. So the Gaussian noise will try to push the model into the direction of this very large value because such an error is impossible. So it must be the model that says that, or it will do other things somewhere. This is visible in plotting 1 minus the CDF. When we reason about the tail of a distribution, the very large value, it's very useful to look at 1 minus the CDF, which is a probability that we have a value larger than some threshold. And we see here, now I'm plotting that in log scale. This was natural scale everywhere. Here I have semi-log, natural on x, log on y, and for exponential we find a straight line, of course. This is the log of this. So. And for the Gaussian, we see it's quadratic, so it goes to 0, of course, very slowly. So we say, if we see, for example, here a value, an error of 8, has a probability of 10 to the minus 16 for the Gaussian distribution, and a probability of larger than 10 to the minus 2 in the exponential, or the Laplace noise. So that's the major difference. All the errors, if we have a number of points that not too large, 1,000 points, for example, is very unlikely to see values that are in this range. So it means the Laplace noise is limited to here. The Gaussian noise is limited to here. Anything above 4 will be considered impossible, whereas here we will allow much, much larger values. Now let's go to why we have Laplace noise. Not surprisingly, we have this model that says, if I do exactly the same as before, I assume I have a model fitting exercise, linear or nonlinear, where I assume that the noise is not n0 sigma square, but Laplace lambda. So lambda is the parameter, but it dictates the value of the variance. Laplace noise has 0 mean, and the variance is dictated by lambda. The larger the lambda, the smaller the variance. 1 over lambda will dictate the value of the variance. Then we have a similar result as before that can be obtained also similarly. No, I don't give the details, but we can look at the log likelihood. I mean, we have obtained the likelihood of the Laplace noise, so we can redo the exercise we did an hour ago of the optimization. And we will find similar things. We will find that if we want to maximize the likelihood of this, first, for a given beta, we need to find for lambda this thing. 1 over lambda hat for a given beta is this estimate of the noise. Now you recognize the L1 norm of the noise. Now it's 1 over lambda, because it's 1 over lambda that gives the variance of an exponential distribution. When we take the absolute value of Laplace noise is exponentially. Therefore, since I know this is what I should, this is my estimate of lambda, no, not therefore, and if we continue with the same exercise, with the same method as before, we will see that maximizing the likelihood is the same as minimizing the residual noise, which is given by this. In other words, if we want to estimate beta with this model, what we minimize is the L1 score. In other words, we find the equivalence here if we use the L1 norm for the noise, which is what is often done in signal processing when, at least in recent models of signal processing, we can interpret that as saying there is IID Laplace noise. We can also give weights, similar as we did here, and then the weights go in the same direction because 1 over lambda now is the variance. So 1 over lambda square would be the variance. So if we want to put weights here, it's similar to assuming noise with those weights on the ith component of the noise. So we have closed the box, whether we choose L1 or L2, least square, or L1, minimum deviation, then we have the interpretation. Here I did that in log scale for L1 and L2. And in this example, there's no difference, or no visible difference here. It gives quasi the same result, not verbatim the same, but quasi the same result, which is quite typical. If you have a good model with no outlier, the two will give the same, which is good in some sense. It means we don't need to worry too much about it. However, the thing might be very different if I have outliers. So what I did here is I corrupted the data with one outlier. So where is the outlier?
6. The other plot.
6 here.
In the other plot.
In the other plot? Yeah.
6 at the top.
Oh yes, we see it here. Yes, thank you very much. So yeah, so there is no outlier here, of course. And here I have a value which is completely obviously false, which is here. Right? Now, because the point is in the middle of the lines, if you need to do a linear regression and there's a point that's completely out, if you have many, many points, you still need to go to be close to the other point. So the two lines will still remain far from that point, which is good. That means the outlier is easily detectable. If the outlier had been at the edge, that would have been a bit more difficult. But look at what happens to the two estimators. Green is least square, red is L1. We see that the least square ping has still been impacted by that. It's trying to get there in a stupid way. It gets below here and higher there. But that's what the mathematics of least square does. If you think about it, if there's an outlier, the score, the contribution to the score of the outlier is huge. Because you take this to the square, and this is to the square. So the contribution is huge. So any minimal change you do that reduces this one will improve the score. Even if you destroy completely the fit for lots of points here. But here what matters is the integral of the errors. So here I have large errors for a large number of points, but I integrate all of this and I square. Since they are small, many squares of many small things is much smaller than the square of one big thing. So this is what happens here. In contrast, you see that this estimation is not impacted. In fact, quasi not impacted here. You see that the values are only the third decimal are modified when we have the outlier that's introduced here. Voila, that's all we will do for today. We will remain with this good feeling that L1 is more robust. What we will do tomorrow is to see how concretely we can do L1 norm minimization and other estimations called the bootstrap. See you tomorrow.